things you've been taught before today. How two lines intersect on a grid in two space. That was grade 10, elimination and substitution. Earlier in the lesson sets, you learned about how two lines intersect in three space. And instead of being three types of intersections, that being intersecting in a point, intersecting in itself because they are the same line, or intersecting in nowhere because they run parallel. With the intersection of two lines in three space, you have a fourth possibility, and that is the skew lines. So going non-parallel but also not meeting because you've got a third dimension, that being the z-axis. What we're doing now is we're moving still in three space because I'm talking about a plane, but in three space we're talking about intersection of a line and a plane. So here are your three possibilities, and then we'll do some examples. So the first possibility is that your line bumps into or cuts through the plane. So remember, a plane is an example, a piece of paper that goes on forever and ever in both directions. The line just crosses through it. Doesn't have to be 90 degrees, it just passes through it. And what will happen in this particular case is you will get one point of intersection. So the line crosses the plane at a single point. In this case, the line and the plane are not parallel, and you would have a solvable equation. Another possibility is no point of intersection. And this is when your line and your plane are parallel and distinct. Parallel meaning parallel, one lies above or below the other. Distinct meaning they are separate from each other. And the line and the plane are parallel and distinct, meaning they never ever intersect. You will get a result that looks like this. And we will get into that in a minute. Just in case you're curious about this statement, this says 0 times a number is equal to a number. Not possible. 0 times a number is always equal to 0. And the third situation is infinite points of intersection, and that is when the line and the plane are not distinct. They are coincident. So you've got two kind of new words. You've got distinct, which means they are separate from each other, and coincident, which basically in this case means the line is lying inside the plane. So it's like drawing a line on a piece of paper. So the line lies within the plane. Every point on the line is also on the plane. And your result this time is 0t is equal to 0, which always happens. 0 times a number is always 0. And that means you've got infinite points of intersection. So let's do an example. So I've got two of them. I'm going to take one away because I know I'm going to need some space. And I've got this little note here that says there's information on the next slide. Notice in this case I've got a line. I know it's a line because I've got x, y, z vector equation, a point, and a direction vector rather than two direction vectors, which is for a plane. And then I've got a plane, and this is in Cartesian form, so scalar form. So let's see what my little helpful hints say. Oh, totally not helpful. Let's go back. All right, so what are the steps to finding an intersection, if any, between this line and this plane? So one of these three situations is going to happen, and we have to figure out which one it is. So we're either going to end up with t is equal to some number, 0t is equal to some number, which is crap, and then 0t is equal to 0, which is always true. So let's see what happens here. First step is me taking this vector equation, and I'm going to turn it into its three parametric equations. So I'm going to do this in red. So this is the line. So x is equal to 2 plus 3t. X, x, x. Y is equal to negative 3 plus 1t. Y, y, y. And z is equal to 1 plus 2t, z, z, z. And then we have our plane. Remember your plane abbreviation symbol. And the plane, oops, don't know what's happening here. The plane has this Cartesian or scalar equation. But the cool thing is, now that I've set it up with parametric equations, is I can take the x and replace it here with its parametric equation, meaning the x is going to disappear and I'll end up with t's. I can do that with the y, so the y will disappear and we'll end up with t's, and the z will disappear and I'll end up with t's. So I'll have no other letters except the letter t, which is kind of what we're looking for. So, carefully, here is me substituting the x, carefully substituting the y, and carefully substituting the z. Don't lose the 12 and don't lose the equal 0. So now I can do grade 9 math, only higher level. So I'm going to multiply these brackets out carefully. And then I'm going to collect my t's on one side and my numbers on the other. So 6 plus 9t plus 6 minus 2t minus 5 minus 10t plus 12 is equal to 0. So I'm going to collect my numbers and collect my t's. I've got 9t minus 2t is 7t. 7t minus 10t is negative 3t. So I already know that it is not this situation because I don't have 0t. And I already know it is not this situation because I don't have 0t. I have negative 3t. Now the numbers. So 6 plus 6 is 12. Plus 12 is 24. Minus this 5 is 19. Oh, yes. Whew. 6 plus 6 plus 12, 24, minus 5. Yes. So t's on one side. And I'm going to leave this in fraction form, even though that might annoy some of you. Did it for the third time, I think. Negative. So that's positive 19 over 3. I am in the middle of a hand cramp. So right now, before I finish this off, because it says determine the intersection, if any, of, I know that these two intersect in a point. So I'm going to say in the point and get back to you in a second after my hand cramp disappears. Well, I have no idea why that came on so quickly, but as soon as you end up with t is equal to a number, you know that the line and the plane intersect at a point. So you've got this situation, only you don't know what angle this situation is happening in. The thing is, it's not good enough to say, oh, it's just some random point. What you now have to do is you have to take this t value and you have to sub it back into your parametric equations so that you have the specific x, the specific y, and the specific z that make this point. So I'm going to see how much I can fit in here. So 19 over 3 is a t. These 3's will cancel out, and it'll be 2 plus 19, which is 21. So now I have the first coordinate because this is a point. Next one, y is equal to negative 3 plus 19 over 3. Common denominator is needed here, so negative 9 over 3 plus 19 over 3 is equal to 10 over 3. And I have the luxury of doing this. So now I'm going to take the 19 over 3 and I'm going to put it in for the z to get my final coordinate. So unfortunately, just because it is a point doesn't mean it's a nice point. It just means it's a point. So I'm going to turn this into 3 over 3 immediately, plus 38 over 3. So that's 41 over 3. So I can say now that it intersects in the point, round bracket, 21, 10 over 3, 41 over 3. And like I said, not always pretty. I don't know if you noticed up here that I got inconsistent with my brackets. And that's okay, except in your therefore statement. So if you do that, I will not harp on you too badly. What I am going to ask is that your direction vector has square brackets around it. All right, so next question, last question. Will either be, my guess is, it'll either be this situation, which is never, so that means they never intersect, or this situation, which is always, in which case you get to say there are infinite many points of intersection, or you can say the line and the plane are parallel and coincident. So it's not good enough to say parallel, because it could be parallel and distinct, or it could be parallel and coincident, so you do have to be specific. All right, back at a flash, still hand cramping. Okay, do you see how this question is different? Still got our plane, still got our scalar or Cartesian equation, but the problem here is that I don't have a vector equation that I can turn very easily into a parametric equation. I have the symmetric equation. So I'm going to show this with a little bit of work in case going backwards for this isn't a strong suit. So the line will have x minus 2 over 3, and you can equal that to not this or this, but to any parameter you want. So I'm going to let it equal to t. Then I'm going to do a half cross multiply, so I'm going to fling by multiplication that 3 up with the t, and then I'm going to isolate x. And it doesn't matter the order, so I'm going to put the 3t first and the 2 second. Then I'm going to do the same thing here. So y plus 5 is equal to t. No flinging or half cross multiplying or needing to multiply. With this one, it's pretty simple. There's the y. And the z, so z subtract 6 over 8 equals t. And some of you can do this all in one step carefully. I am not one of those people who can do things carefully. So I show all my work. So I have my parametric equations now. X, y, and z. And now I can take the Cartesian equation of this plane, and I can take those parametric equations and sub them in. Now I've decided to use t because my t's don't look like plus signs, but if you did, you could make them equal k. You just can't pick two different parameters, it's only one. So let me substitute carefully. So there's x. Y stands alone, so I don't even need a bracket. There's z. Don't lose the tail end of the equation. And now I'll multiply where I need to multiply. So we have 15t plus 10 plus 1t minus 5 minus 16t minus 12 plus 2 is equal to 0. So 15t plus 1t is 16t, minus 16t is 0t. So I do have one of these two situations. So now I'm about to collect up the numbers. I'm either going to get this or I'm going to get this. So 10 minus 5 is 5. 5 minus 12 is negative 7. Negative 7 plus 2 is negative 5. Let me double check that. 12 and 12. Yep, I'm good. So now I go and solve like I forgotten what my rules are, as in these rules. So I'm going to say, okay, 0 times something is equal to a number. So this is always false. This is not possible. This is the never. So that also means that I can say, therefore, the line and the plane never intersect. And we can go one step further and describe what's happening. So therefore, the line and the plane are parallel and distinct, meaning that one is flying up above the other. So I forgot to check my little notes. So this came from here, so that was my rearrangement. The line and the plane intersect. There will be a value of t that gives us the point on the line that satisfies the equation of the line. So we subbed the above into the Cartesian equation of the plane to see if a value of t occurs. So we subbed that in. So those are your steps. If I'm writing stuff down, it's probably that, because this is very specific to a question. All right. One more thing to look at, even though there's no more examples, and that is, what happens if it is you got your 3 parametrics, you got your Cartesian plane, and you sub them in, and you do a whole bunch of work, and you end up with 0t is equal to 0. What kind of therefore statement are you going to give? The reason I want to go over that is because I've got a really dynamite therefore statement here. It's specific. It says that the line and the plane intersect in a point, and that's what the point is. And this one is that the line and the plane never intersect, and that looks like the line and the plane are parallel and distinct. So what kind of therefore statement do you write when you end up with 0t is equal to 0? And when that happens, it's always true. Always true. So you get to say, therefore, the line and the plane are parallel and coincident, which is you describing how they look on a page or in space, but that doesn't tell you where they actually intersect. So the first one was intersecting at a point, you tell me about it. The second one, not at all, so you don't have to tell me about it. So in this one, you get to say the line and the plane intersect and they'd intersect in a line and you would either state the vector equation the parametric equation. And because this is a line, you could either state those two or the symmetric equation. So you'd have to tell me the name of the line, which is going to be in the question either as symmetric or vector or your converted parametric, unless I'm nice and give that to you in the first place. So that's what your three therefore statements look like based on your three different results, based on your three different pictures. Okay, so suggested questions right here. So 1, 2, 3, 4, 9, and then 14a. So that is that. And the next thing is, I believe, intersecting a plane with another plane.